Okay, what we're going to do today, this is actually the last big lecture. The rest of the quarter is project work, an exam, things like that. So this is actually the last big lecture for any new content. We've got this is our strain gauge out. We got it back out. Last time that we looked at it, we had built this part, which was the Wheatstone bridge, which was a balanced circuit that becomes unbalanced whenever you strain the strain gauge, and you get a little voltage differential across what I've got here is this purple and blue wire. And now I've got this thing. It's a little cluttery, so we'll have to draw a picture of what's actually going on there. But this little chip is actually it's 2 op amps built onto one chip in a dip package. I guess the P is package, isn't it? So anyway, there's 2 op amps inside there, and we've built a little circuit around it. So we'll look at that, how that works. We'll look at these tools, these little Boar gauges. I don't know if you can call them gauges or not because they don't actually measure anything, but you can use them to measure interior diameter. I guess it doesn't have to be a diameter, but interior dimension. And we will talk about analog and digital signals and a little bit about converting between them. In fact, why don't we do that first? To me, it's the more, I don't know, like lecture-y part, so we'll do that first. And then that we'll get these out of the way for now. Come back to that. Let's see, there we go. All right, so analog and digital signals. We've talked a little bit about them already. Let me see if I can find where I put my notes for that. There they are. All right. I don't know if we need to look at any of the notes. There might be some. But analog and digital. We don't need to talk a whole lot about this, but a little bit just so we have an idea of what's going on. Actually, let's get the Arduino back so we can point out something on it. All right, so one of the reasons we like using the Arduino, remember it's underneath this shield. This shield is just for the SD card. But underneath there's Arduino Uno. One of the reasons we like the Arduino Uno is that it can both measure digital and analog. You don't have to have a separate piece of circuitry to measure analog signals. So these 6 ports over here, pins, are able to take analog signals directly in. So in this case, it's taking a signal from whatever I've got over here in this circuit, a voltage. These are digital pins. They can actually be digital in or out, so you have to assign them beforehand. Are they going to be outputs or inputs? The analog can only be inputs. You can't do an analog out, at least not that way. You can kind of fake an analog out over here. We're not really going to talk about that other than to say it's called pulse width modulation. In general, though, these digital pins, if they're an output, they can either be on or off. And so usually for the Arduino, on means it's outputting 5 volts and off means it's outputting 0 volts. As an input, they can measure, but when they measure on or off. You know, is the thing that's coming into them. So is this little white signal right here, is that wire high or low? Is it on or off? And that's all the information you get. But when you measure on analog, you get a range of measurements. Now, in the Arduino, these analog measurements that you are taking become digitized, so they do become quantized, so that they aren't the full range of values from 0 to whatever your maximum is, but they are individual little steps inside there. But there's still more than just on and off. So the biggest difference between analog and digital is analog is going to be a continuous signal. So it's the one where, you know, you've got a continuous signal. I'm just drawing a sine wave signal here. And digital is it's either off or it's on. So a lot of times off is low and on is high. So this would be a low signal. This would be high. And same way, either outputs or inputs, it's either low or high. There's no in-betweens in there. And like I said, you can fake the in-betweens with this idea called pulse width modulation. In fact, if I had the shield off of the Arduino, you'd see, I think it's 4, 5, I think, no, maybe 6. I think there's 6. Actually, here's a picture. Let me show you. Right here. This one, 9, 10, 11, 3, 5, and 6 all have this PWM. That's pulse width modulation. Basically what you're doing there is you are turning the pin on and off really quickly, and depending on the duty cycle, how long is it on compared to how long it's off, you will create something like an analog signal, so something that's not just maximum or minimum, it's somewhere in the middle. So you can kind of fake analog type outputs with digital outputs, but it is fake in the sense that you're just turning it on and off really fast at a certain pattern. All right, so that's the analog digital, whoops, get that off there, analog digital idea. Let's see, for examples, this would be an analog signal. You know, that needle can exist at any point in there. You know, it doesn't skip steps. It can be at any point in there. Now, it does have some limiting resolution that I can't resolve it at some point. You know, I can't tell past, and it's showing me on the dial here, 0.001 inches. I can't really, I guess I could estimate the 4th decimal place, but I couldn't estimate it anything other than really 0 or maybe 5 or 1. You know, 0 high or halfway in between the two. So basically I could estimate if it's halfway between two of these little lines here, but I couldn't say that it's 2/3 of the way between the line. I guess I could try, but at some point I just can't resolve the measurement anymore. But that's an analog one because that needle can exist anywhere on that dial, versus this, you know, when I turn this guy on, I only get 4 numbers. That's all I get. So it is digitized, and this is a digital multimeter. They do make analog multimeters that have a dial like this one, a meter that sweeps across there, and you can have an analog reading. All right, so analog is the continuous, digital is quantized in some way. Let's see. We already talked about the idea that on the Arduino, those pins on the digital side could be inputs or outputs, and you have to decide beforehand in your code, are they going to be inputs or outputs? In fact, you have to set them up as being an input or output. The analog, like I said, is only input. Let's see. On the Arduino, it has, like I said, when you do use an analog read, remember that's the command to read an analog signal. And then there's some pin number. I think we have it on 0 right now. So when you do this command, analog read pin 0 or pin 1 or up to 5, what's happening here is an A to D conversion. So an analog to digital conversion. So I've got my analog signal coming in to pin 0 through this gray wire, and if I plot the analog read, so if I take this and plot it on my serial monitor, then I actually get a digitized version of that signal. But it's not just on and off. So there's a conversion that happens here based on the chip that's doing this conversion. On the Arduino, it is a 10-bit analog conversion. So it's a 10-bit analog to digital conversion. And you can get different, you can buy these chips separately. So if you're using something like a Raspberry Pi or some other controller that doesn't automatically take analog or doesn't have an A to D converter on it, you can buy them separately. They're really cheap. They're just little chips, a lot like this one, you know, or at least they look like this one. They don't operate the same way, but they look like that, or they can look like that. And you can get different sizes, I'll say. So you might have a 12-bit or a 16-bit or whatever. So what the bit is doing here, the 10-bit, is, remember, in binary, you have 2 states. So you have on and off. And so 10 bits means that you have 10 bits that can either be 0 or 1, all strung together that represent that analog value that was read. Now on the Arduino, you can have, or well, in any system, but on the Arduino in particular, you can have a reference that you compare what you're measuring to. So that reference by default is 5 volts. You can also default it in code to be 3.3 volts because there is a, let me show you on our picture here. Here we go. So see how you've already got a 3.3 volt here, and then you've got a 5 volt here. So you can switch it in code to reference this 5 volt as the maximum measurement that could be measured, or 3.3 volts, or you can switch it over to this VN, and whatever voltage you've put into the Arduino will be the reference volt. And that could be a lot of different numbers. Up to, there's just a maximum. I think the maximum you can put in here is 12 volts. A lot of times though, you would, unless you were trying to measure a larger signal, you would actually want this to be smaller, because what doesn't change is the 10-bit part. So you are stuck with a 10-bit conversion, and that means that you have two, each one of these has two states, 0 or 1. You know, this would be 0, 1, 1, 0, whatever. They can only have two states. To the 10th, in this case, equals 1024. If you do 2 raised to the 10th power, that's 1024. What that is the number of steps or number of little positions that can exist between 0, your bottom reference voltage, and in our case 5 volts, the upper reference voltage. And so you basically have 5 divided by 1024. Now, a lot of times there are 1024, except that, remember, we count from 0 to 1023. So 0 volts represents the 0 over here, or 0 here represents the 0 volts, and 1023 represents your reference voltage. So in our case, if you don't change anything, that it defaults to 5 volts. So this would be 0 volts to 5 volts. So each one of the steps in between there is 1/1023rd of 5 volts. So let's see what that is. Here's a calculator. So if I did 1023 divided by 5, 204. Wait, 204. If you divide, I did that backwards. 5 divides, like, that doesn't make any sense. There we go. 5 volts reference divided into 10,000 or 1023 little steps. Each step is 0.0049 volts. That makes more sense. So I could never measure any smaller than that, really. So each, I'll call them steps, but each division, or the resolution would be a better word. But if I know that I'm not going to be measuring anything larger than maybe 3 volts, I could change this reference from 5 volts to 3 volts, and the same setup, the same Arduino, same everything, but I'm changing the reference for it. 3.3 volt reference divided by 1023. Now each one of the steps in this division could be as small as 0.0032 volts. So I've changed the smallest amount that I could measure. So there are reasons to change that reference voltage, but you do have to be aware that if I tried to measure a 5 volt signal with a 3.3 volt reference, I would just get 3.3 volts. It can't measure any higher than the reference, and so it would become what's called saturated. So by default, the reference is going to be 5 volts. In code, you can change it to be 3.3 volts or whatever you've got going into the VN terminal. I've got some equations here. I don't know that I'm going to show them. So these are simple converters. We've got the digital output. These are two of the same equations solved for different variables. So the digital output are the corresponding voltage for a digital output. There is that N here, this capital N, that is how many bits is your converter. So for us it's 10 bits. And the 2 is because it's a binary converter, so they can only exist in either zeros or ones. And then all of these V's and everything, they're described down here, but they're analog input voltage, upper range, lower end, all these different things. This is just an equation that will let you convert. It's basically doing the same thing as this equation. This one just already has the reference voltage built in. It already has the 2 to the 10th power built into it, and then analog read is what the input to the converter is. So I don't want to spend too much time looking at that, though. It's kind of confusing a little bit. Another part of this, well, it's not confusing. It's just got a lot of V's, VI, VRU, VRL, and all that. So if you put numbers into it, it makes more sense. The other idea here that we have to deal with this is that you do have some error. So there's quantization error. So quantization meaning that you are taking a continuous signal and quantizing it, or making it exist in only certain little increments. For instance, if we had a 3-bit, let's do a 3-bit converter, so that there's only 3 of these. So they would be zeros, all zeros. It's just off, and then 001. I'm only doing 3 bits so that I don't have to make so many marks on here. And then the next number is not 002, it's 010. These are binary numbers. If you don't know exactly how to count in binary, that is totally fine. We did do a little bit of base transformation back on exam 1, very early in the class. I'm at 101 right now. And then 110, and then 111. So there's all 8 different possibilities. 2 to the 3rd power is 8. So there's all that, 8 different possibilities. Now, and then across this axis, we would have the voltage. If I have a 2 to the 8th, or 2 to the 3rd power, so a 3-bit converter, then I only have 8 options down here for the reference voltage. I have all the way off at 0, right? And then I have, let's say that our voltage reference is 5 volts like it normally is. 5 divided by 8 is 0.0625. And then times 2, 1.25. Let's do plus 0.625. 1.875 plus 0.625. There's 2.5 volts. And so yeah, I think you get the idea. I'm adding 0.625 every time. That's the minimum number I can resolve. So if I try to resolve a number that is at 0, I get 0. I get 000, so it's 0. But until I try to resolve a number, an analog number greater than 0.625, I continue to get 0. So all the way up to over half a volt, it measures as 0 on my analog to digital converter, because I've only got a 3-bit converter. I don't have that many little spaces in between here. Now on the 10-bit converter, I only have to get over 0.005 volts. But on a 3-bit converter, so this is where the bit level of the converter actually becomes important. I don't even know if they make a 3-bit converter. This is just for an example. The same thing does occur on these larger ones, but these gaps are obviously much smaller. From 0 to the next number is 0.00489 volts, not 0.625 volts. Then when I get to 0.625, I suddenly read, oh, now it's going to give me this value, 001. But it does that all the way to 1.25 volts. So from 0.625 to over 1 volt, I get the same digital output. And then so you see these little steps all along the way. Those are the quantities that it can be. That's how the signal is quantized. So you have numbers that, if your number is right in this gap between two of these stepping points, then it's just going to read as if it's the lower value here, all the way up until the next step. And so there's a lot of error built into that. You can actually reduce the error a little bit by adding an offset. So let's see, how can I show that? Maybe if I did a different color. So I can add an offset that is basically half of this. So this would be an offset in the signal itself that, maybe I add 0.625 divided by 2. So I add half of this as an offset. And what happens there is it just shifts the measurements over. So the offset shifts everything over. And now I can at least measure plus or minus on this. So instead of 0.625 plus the entire range, I have plus 625 plus or minus that range. So it makes it a little bit better. Now at the very end up here, I actually get 1.5 times the error at the very top end. Most of the time, you're not trying to measure at the very top end of your converter, your reference voltage, but I guess you could be. So this little offset sometimes occurs, or it doesn't occur, you create it so that you have it's called a 1/2 LSB. So LSB is least significant bit. So in our binary conversion number here, the least significant bit would be this one, because it has the least significant effect on this entire number, because it's only a 0 or 1. Obviously this one is the most significant bit, MSB. So this offset that I've added would be a 1/2 least significant bit offset. And you add this to the input voltage. So basically you add that to the analog signal you're measuring, and then you added it. You added 0.3 volts to the thing, so that it's offset by that 0.3 volts, so you can subtract it out later computationally. But sometimes you'll see that, so that the error, instead of you have 0.625 plus this error, you have 0.625 plus or minus half of that error. So that's better in most senses. There is a lot more to this type of stuff, but I don't know that we need to know more about it. Like, we don't need to know exactly how the A to D conversion happens. There are a couple of key things we do need to know, like practical things we need to know, is that A to D converters are pretty linear, or they are linear in their range, but they don't work outside of their range that they're meant to work in. So if I've got a 5 volt reference, then I cannot measure any signals larger than 5 volts. They are thermally stable. I said they're linear. Sometimes at the very low end and very upper end, there are little bits of linearity. And in general, most of your sensors are like that. You don't really want to work at the very extremes of your range. Let's see, what else would we need to talk about for these things? I don't think there's... so I linked on Moodle a whole page of things that you can go through and read. Most of it is lots of little details. I think we actually have talked about the bigger pictures already of what we need. I guess we can work through this little sample. It's not even a sample. It's basically what we did here. But just so we have the idea down for sure. So let's say we have a 12-bit converter. Let's get a new page. 12-bit converter. So the one on the Arduino Uno is a 10-bit converter. That's probably a good test question is, what kind of converter, analog to digital converters on the Arduino Uno. It's a 10-bit converter. What if we have a 12-bit converter? So a 12-bit A to D converter. It has an input range of -10 to +10 volts. So it actually has an entire range of 20 volts, but we've shifted it so it can actually measure negative. We want to find the resolution error, so basically what's the smallest thing we can resolve for this thing. So input resolution error. So it's going to be plus or minus. We don't know, it could be on either side. 0.5. And then our range is actually, our maximum value is 10 volts. And we're using that equation, basically we're using that equation here. This equation basically. All right. So plus or minus 10 volts, plus or minus 0.5 times 10 volts. And then the lower range is actually minus, normally there's a 0 here, but this particular one has a negative 10 volts. So that gives me my 20 volt total range. And then it was a 12-bit converter, so 2 to the 12th power, but you subtract 1 because you actually start counting at 0 with all of these things. Whereas if you are counting normally, you normally start it at 1, but in most electronics and software, you're going to start counting at 0. If I solve this equation over here, I get plus or minus, because it can be an error on either side, 0.00244 volts. That's very similar to the deal over here, but we are doing plus or minus. So basically, if you didn't put the 0.5 and plus or minus, that would be the resolution, and then there is error on either side that we can calculate with half of that entire. In this example, it was 0.625, but we could have plus or minus on either side, but only half of it on either side, right? I think there's more for you to read, but I don't want to just read it. All of it's just information. The main idea is that when we work with digital electronics, but with analog signals, we have to quantize them. We have to convert them over to a digital signal in order to do that. And when we do that process, when we take the analog signal and digitize it, we stand the chance of losing some of the information because of the bit size of our converter. 10 bits is actually a relatively small converter, but even it, with a 5-volt reference, had a resolution of 0.005 volts. So that's generally pretty small, but sometimes you need to measure even smaller than that. So you do have to be aware of this error that does occur when you take analog signals and try to digitize them, that there can be a little bit of error. There's maybe a sampling rate where it can't convert it fast enough. I actually don't know the frequency that these A to D converters on the Arduino can work at, but they can only convert at certain rates. At some point, you're trying to convert too quickly. A lot of times, though, these analog signals are slow enough that that never comes into play. Particularly on this one with the strain gauge, it's not going to ever change fast enough that we can't capture what we want to capture. But there could be some signals that are too fast to convert with an A to D converter. All right, I think that's enough about analog to digital conversion. You just need a big picture of what's going on there. Let's go to our strain gauge. So like I said last time, what we had done is we built our bridge circuit over here, and we were able to measure the voltage across this bridge. Let's redraw the bridge so that you remember what it looks like. So the bridge, this part over here, is, wow, that one doesn't work very well. Let's get another one. That's better. It had 5 volts going in, and then some resistors going to ground. These resistors, the ones that are actual, resistors over here, kind of off the screen. So the ones that are the resistors, they are 120 ohms. Far close to 120 ohms. We went through and I had maybe 3 or 4, and we found the pair that were closest to each other at, I think they were like 119 point something, but they were close to 120 ohms. This one is our gauge. It starts out in its normal state unstrained at 120 ohms, and it was really close to 120 ohms. But then when we strain it, it changes either higher or lower, depending on which way we strain it. And then this one is our potentiometer. So it's the little gray box over here. So we can dial it in to being whatever resistance we want. And we set it to basically balance the gauge at 120 ohms. So they start out pretty much all at 120 ohms. And we're measuring over here across this point and this point. So those are the 2 points we're measuring. And we could measure it, and it would change, but it was something like 0.005, or maybe there was another 0 in there. It was a really small voltage that we could measure, and it could go up to maybe 0.01 volts. I think that was it. 0.005 volts. And then when we strained it, as far as I felt comfortable straining the piece of aluminum before it would actually yield, it would go up to 0.01 volts. So not a terribly small voltage, but pretty small. It'd be better if we could get that amplified. So that's where this comes in. So this chip is, let's see if we can get closer to it so you can see more of it. There it is. So this little chip is a operational amplifier, and like I said, there are actually 2 operational amplifiers on there. I can't remember. I think this is an LM5. Let's see if I can look up the number for it real quick, because I don't remember it. Looking through the notes to see if I have it written down. LM358, that's what it is. So this little chip is called a LM358 dual op amp. So there's actually 2 of them on there. And we've got a couple of resistors. Now, I did not have the ideal resistors for what I needed, so that's why I've got 2 here and 2 here. These are both 100,000 ohm resistors, and these are both 100,000 ohm resistors. I have them in parallel with each other, so that, remember, when resistors are in parallel, they divide the resistance. So if I have 2 100,000 ohm resistors in parallel with each other, that equivalent resistance is 50,000, and that 50,000 is important because how you, in this case, I'm using the op amp as a amplifier, and the amount of amplification in the setup that I have here between this bridge and this amplifier circuit is determined by the ratio of these resistors to these resistors over here. So the resistors I have over here are 120 ohms. These resistors are acting like 50,000 ohms. And my gain I'm way off the page just because we're zoomed in, aren't we? So 50,000 ohms divided by 120 ohms is the gain. The gain equals, let's see, I don't remember the number. 50,000 divided by 120 is 417. So what that means is that the signal that's coming out of my bridge circuit, so the one that was before it maxed out at like 0.1 volt, 0.01 volts, I am multiplying that by 417. So if my maximum was 0.01 times 417, that should show up as a 4.17 volt gain. 4.71 volt, not gain, but 4.71 volts. It should be showed up multiplied. Obviously I can get more gain if I change. I can't really change this 120 ohms. That is the from the bridge, which I need them to be 120 because my gauge is 120 ohms, which I can't really change it very easily. There are other gauges with other resistance values, but I don't know that there's any that are really lower than 120 ohms anyway. So I'm kind of stuck with the denominator over here. So what you do is you go in and you kind of get an idea for what is the maximum voltage I'm probably going to put into this. And I do have a limit. These op amps have the same kind of thing where that the A to D converter, they aren't A to D converters, but they have the same idea of where you power them, so you can kind of see, well, it's kind of hard to tell where here's the power coming in on this line, and then it's grounded over here with this brown wire. So it's powered, and it's powered right now through the Arduino from 5 volts. So the Arduino is sending 5 volts to this op amp. And I can never multiply my voltage that's coming in to something greater than 5 volts. In fact, I can't even get all the way up to 5 volts. I can get to like 90% of 5 volts. It becomes saturated before it gets to the very top. So if I get 50,000 as my resistance of the resistors over on the op amp side that are creating the multiplication, then a gain of 400-ish or somewhere, you know, because these, I didn't measure these, or these aren't exactly 50,000, but they're somewhere near that. A gain of 400 puts me right around the upper limit of what this op amp can do. So I'm taking maximum advantage of the amplifier circuit. Let's get a picture of the amplifier circuit so we can kind of walk through it. Right here's one. Right here. So here's our bridge. Now in this picture of the bridge, they've kind of got the strain gauge down here. It doesn't really matter where the strain gauge is, but this is where we put it. Uh-oh, I think I forgot to divide by 2. Well, anyway, we'll come back to that. So my gain may only be 200. Still will be okay, but that does mean I could have had more gain because I don't think I remember dividing by 2. So this triangle is the op amp right here. It has an inverting terminal, so the negative is inverting, the plus is non-inverting. What that means is that if you put your signal into the thing in a way that comes in as a negative number and you send it into the inverting terminal, it comes out as a positive number, and vice versa. Here is that RF. This is what I have for 50,000. I also have 50,000 here. And then I didn't do the divided by 2, so I think my gain is actually only like 220 or 210-ish. So we might only have about half the gain that I thought, which we could fix by just taking out one of our resistors and going back to 100,000 here and 100,000 here. Right now I have 50,000 both of those. So we might just pull both of them out, and because I forgot to divide by 2, I believe. Sorry. We'll do that in a second and see the effect of it. All right. there are a lot of these configurations, right? Lots and lots of configurations for op amps that do different things. You have them generating sine, or actually those are coupled with AC. Here they're generating pulses. We talked about a little bit on the sampling rate lecture. We talked about needing to filter your signal. There should be some in here that are filters. Let's see if I can find one. It's probably scrolling really fast on your screen and you can't see anything. Here's one. Here's a low pass filter. So that would mean that it lets lower frequency signals go through and higher ones not go through. And you can change the ratio of capacitors and resistors to figure out, or to set that pass point. Here's band pass. So that's it lets the middle range of something go through, and it chops off the lower and upper frequencies. And you set those two, and basically it's just this guy coupled with another, so a low pass and a high pass filter stuck together. So you can use these to filter your signal. That's a little more important when your signal is very noisy, or you're trying to sample it and you don't want that aliasing from higher frequencies coming down into your signal. There's a lot of different things. Here's an instrumentation amplifier. That's a really common setup. But we have this setup. So bridge current amplifier. There's our bridge, and we're going to amplify that. Now it says current, but we're actually going to measure the voltage. Oh yeah, I think I did this, which is the non-inverting, but we built this one, the inverting. All right, so let's go over, actually let's fire up the Arduino code that's behind this thing. It's super simple. We start a serial communication, we read pin 0, we set up a variable here as an integer. We print the thing we read. So again, it's going to print a number from 0 to 1023 because we have a 10-bit converter. We wait for 10 milliseconds and do it all again. So we just keep reading that pin 0 over and over again. All right, so let me plug this in and see what we have. So there it was. We can get our, we have a light on it over here. I'm gonna have to get where you can see most of this. I don't know if we can see it all at one time, but there's the strain gauge. Let's watch our serial plotter so that we can watch a graph of the thing. All right, so there's the graph. Basically, it's sitting at 20, which is more or less 0, right? So we do have some random spikes, a little bit noisy, but they're essentially nothing. So if we strain our strain gauge, I'm going to try to keep it on the screen and bend it, and there you can see I'm doing the pulsing there. We got up to around 600. So remember, our maximum was 10,000 or 1,023. I keep saying 10,000, but it's 1,023. But that was because I forgot on my gain that to divide this by 2, the delta over 2. So there's a divided by 2. So if I pull out this guy and maybe this guy, now these are 100,000 ohm resistances each. And so my gain should be back up where I wanted it. So let's see. Let's go back over here. Now my baseline is at 9. It was at 20 before. Now when I flex this guy, there's saturation right there. See how it maxes out? Right? I can't make it go above that. That is, I've saturated the op amp. So, and I saturated it at some number, I don't know what number that is, but 790 or something. Let's see what that corresponds to. Maybe it's, let's say it's 790. We could plot the actual numbers, I guess. Let's switch to the serial monitor and see what number that is. All right, so there's our baseline. Let's max it out and see what that number is. 760 is what it is. All right. So 760 divided by 1023 times 5 volts, that's 3.7 volts. So at 3.7 volts, I'm actually saturating the op amp. I'm sending it 5 volts, so I'm actually not even getting close to the 5 5 volts out of there before it saturates. So I'm going to go ahead and put my other resistors back in here so that I switch my gain back down. It seems like I accidentally had it right the first time, or better the first time. But that's a thing that can happen where you build one of these amplifier circuits and you think, oh, well, I'll just amplify it up to 5 volts. But it turns out this op amp itself saturates at 3.7 volts, which is only 74%, 75% of the reference voltage, the 5 volts that I went in there with. So now, oh, I did something to it that's caused it to be crazy. There we go. I think I had the resistors touching each other, and it was just shorting it out. So there we're back to 20. I actually like the plotter because you can see what's going on better. So let's flex it again. I can still saturate it, but it takes a lot more effort to saturate it than it did before. But that is the voltage associated with the resistance in this strain gauge here, which is associated with the strain in the beam. So now I could, if I wanted to take this further, and this is the general idea of how load cells work. I could calibrate this beam, put it in a fixture, calibrate it so that it was measuring force. So I could start to figure out how much force is applied, but I'm actually measuring a voltage, then amplifying the voltage, then converting it to a digital signal. So there's a lot that goes on in one of these sensor setups. But I could measure force. I could relate it all the way back to a force through the strain in the beam. All right. Let's see. I don't know that there is more that I want to talk about with the op amps, other than we talked about the fact that they can get saturated. Oh, we should talk about this part probably. Probably should talk about this. This is the pin out for the LM358 that we have. There you can see the 2 little op amps on it. There's an A and a B. This is kind of good because it is possible to burn up one of these little op amps. You hook it up wrong, or you put too much current directly across it and it can burn up. The ideal op amp has an infinite resistance across it, but that's the ideal op amp. So it is possible that maybe you burn up op amp A, maybe op amp B is still good, although they do share the same power. So it's possible that you burn one of them, you burn both of them, but it's also possible that one of them is still good. But what I did is I powered, this is 5 volts, the VS, this is ground on pin 4. How you know where 1, 2, 3, 4, 5, 6, 7, 8 are is there's a little circle or a notch. Now these have a circle. If we go back to the close-up view, it's actually covered up by these wires. It's hard to see. Maybe if I zoom in really close, you can, there it is. That little circle, sometimes there's a notch up here that's like physically cut into the chip, and that tells you basically where the top is, and it tells you where pin 1 is. So that circle, it's way smaller on the diagram here, but sometimes there'll be a notch in the chip. That tells you where pin 1 is, and then you can count around so that you know what to connect to what points. So the output, that's where my analog read is going. Also, there are some of the resistors in our circuit actually go to the output. See, this resistor connects to the output. I don't know why there's 2 of those. And then the inverting input, that's the one that has the negative sign on it. And then the non-inverting input, that's the one that has the positive sign on it. So you really just use these 4 and number 8. And then these 3 would be if you were using the second op amp on that chip. They're super cheap. One of them is 35 cents. If you buy 5,000, they're like 9 cents each. So they're not expensive chips at all. And that's in this package. There are other surface mount packages that are probably even cheaper than that. Here's a little picture showing what we experienced in our plot. That maybe, well, this is even using 5 volts. That you give it 5 volts power here at VS. That's what it's going to use as its power. It can't amplify anything more than 5 volts. But it can't even get to 5 volts. We found out that it gets to 75% of 5 volts and then it saturates, and it can't do any more than that. But between 0 and that point, it's pretty linear. There's a nice linear gain from the op amp. Let's see if there's anything. That's just an example for calculating the gain on that. You can work through that if you wanted to and see how it amplifies the circuit. That's not quite the circuit that we're using. It's similar, but there's different values. Also, I think they might have something backwards here because they've got R2 as 1,000 ohms and R2 as 120. So I think they got something wrong in that. So don't look at that. So, but these little op amps are useful not just for amplifying. They have a lot of different uses. They're really cheap. Most of the common uses that you would use them for are to amplify something like we have here, or as a filter. We didn't use this one as a filter. Maybe there is another one on here. You could use the other one as a little 60 hertz filter, so that anything above 60 hertz. 60 hertz is the frequency that most of our electronics from the wall, like the wall outlets and all the wiring in your house, operate at 60 hertz, assuming you're in the United States. And so a lot of times you'll see a 60 hertz filter associated with these measurements to try and eliminate that stuff, so that it's not even riding on your signal. You don't see it at all. Now, we weren't sampling really fast enough to detect it anyway, but sometimes you are. And then so you could do a 60 hertz filter, and then use the other one as the amplifier filter, and so that would be a nice little pair. One of them being the noise filter, and one of them being the amplifier. All right. I think the last thing we're going to do is we're going to look at our little tool that I brought out, just because I like showing you actual tools that you might not have seen before, or maybe you have, or maybe, I don't know. But this little guy, actually, they come in a set. There's a whole bunch of them, and we zoomed way too much. There we go. So we've got larger ones down to tiny ones. They come in. Now this set, there are different. I wrote this down as a bore gauge. There are actual bore gauges. So bore meaning a hole that's drilled into something. There are bore gauges that are similar to this, and they actually have a dial back here that you read them directly. These, and those are maybe, the cheap ones are maybe $50 or $60. These are like, the whole set is $20 probably, something like that. They're not expensive, but what they do is they have this little I don't know, screw back here, and you can release it, and they are spring loaded, and so you pull them in, tighten it down, they stay in there, and then let's say you want to measure an internal size. You put the gauge down in there, release the spring, kind of move it around to get it set, tighten it down, and then you pull it back out, and now you use something like your calipers to measure where it was at. So 0.8, pretty much 0.8 inches, 0.801, 0.8001 inches. So that you don't measure directly with them, but you can get good measurements with them. Now you could, go in and measure with your calipers also, but maybe there's something really far down in there. Maybe it's stepped down, and there's a smaller diameter way inside there that you need to measure. These are, able to measure 3 or 4 inches down into something, to get a measurement that you couldn't really get any other way. And like I said, they're pretty cheap, or at least I don't like the word cheap. They're affordable, and they work fine. You spring load them. Actually, this one's already tightened down. You spring them, put them in the object, extend them, clamp it back down, and then take it out and measure that distance. And you have a pretty accurate measurement of an internal diameter. Like I said, there are some that are the same idea, but they themselves are a gauge. Those are pretty expensive. They do have really tight tolerances from what I remember. I don't have a set like that, but they are maybe down to 5/10 thousandths is their kind of resolution limit. This one is limited to the resolution of whatever tool you're using to measure them with. So I can measure down to a thousandth of an inch with this caliper. They do have slightly domed ends on them so that you get just the tip point there when you're measuring. So you do have to be careful if you were measuring them with calipers that you're not, I don't know why you would, but that you're not just using the very, very end edge there, that you are measuring inside the center where the maximum, that radius is. So they're kind of cool. This is, I don't even know if this is a branded set. I don't see a name on it anywhere. No. But I'm sure they make slightly better ones, although there's not a lot to them. They're just spring-loaded little T-bars that you clamp down, and as long as they hold their size as you take them out, then they're perfectly fine for measuring an internal diameter that may be difficult to get to any other way. It's particularly true when the exact feature you want to measure is way inside there, or maybe there's a step down inside the thing, so there's a smaller diameter inside there that you just can't get to with calipers or something. So they're a nice little tool for measuring that kind of specialty. You don't do that kind of measurement very often, but if you do, that's the way that you can do it. All right, so what we have left is basically project work. We have an exam on the 5th. Exam 2 is on the 5th. It'll operate basically the same way that exam 1 operated. Then the last 2 days, the 10th and the 12th, are your presentation of your longer term project, the one where you're collecting data for 3 days and you're going to analyze it. I think probably you have to start collecting that data pretty soon if you haven't already started it. On Moodle, it says that this coming Thursday, you're supposed to demonstrate your system working. All I need there is I'll set up a Zoom so that if you want to ask questions or if you want to show me in person, that's fine. But if you just want a video, here it is, it's working and it's collecting the data I need. I just need to make sure that everybody has their measurement system operational so that we don't get to the end and somebody has problems. Now, you still might have problems between now and the end, but at least right now, I want to make sure everybody doesn't have problems with their measurement system. So there won't be a YouTube stream on the 29th, but I'll set up a Zoom, but you don't even have to do that if you just want to send me a video. I'll put an upload place in Moodle where you can upload the example of your sensor working in the way that you intend it to work. Basically, that you've got all the parts you need and they all work. But there's no new content. I'll put out a outline for what exam 2 will look like. I'll put that out soon. But the rest of the class periods are really set aside for project work. So this is a lecture lab. We're kind of doing most of the lab work now. You've been doing little things on and off, but most of the work from here on out is you working on your project. And I'll have Zoom, Discord, whatever is convenient for you, so that you can ask questions about those. But I will put out probably a short video about the exam 2 when it's closer to time. Exam 2 is on the 5th. Until then, I think we're good. We don't have any other content we need to cover. I think I might not have. I need to see if I've put homework 6. Homework 6 is the last homework. I don't know if I've posted that one yet or not. It's the last one, though, other than the project. All right, I will see you soon, but I don't think we'll have anything on Thursday. The only thing I would post on Thursday is if I do go ahead and post an overview of exam 2. Other than that, you just need to demonstrate somehow that your project is working, that your sensors are working, you've got all the pieces, you've got your battery pack working, all the parts of it are working, so that I'm relatively confident you can collect your data for the big project. All right, I will see you all later.